Now this is going to be a very short lesson. We're going to talk about the derivative formulae for inverse functions, and we're going to pay particular attention to logarithmic function and also inverse trigonometric functions. We must start from implicit differentiation first, because that's going to be the key technique. That's where everything begins. Here's an example. If you have an implicit relationship between x and y, we can take the derivative of everything, each term. But just remember one thing. Whenever you take the derivative with respect to y by chain rule, y prime pops out. So y prime comes here, y prime comes out here, kind of like that. Because y primes are coming from the chain rule, they comes only once and multiplied only once, you will have to have a linear equation of y prime, so you can actually solve for y prime. Typical technique, get all the y prime term in one side, move everything else to the other side, and then divide, and then we have y prime. Now, the kind of computation we are going to do for inverse function will be a lot simpler than this one. So please be assured it's not going to be too difficult, even though we're going to do some proofs. Here is the general theorem for inverse function, and here's the definition, derivative formula for inverse function in general. Derivative of an inverse function is 1 over the derivative of the original function evaluated at appropriate place, and of course that's inverse function. Or you can express this one as 1 over f prime of y, because after all, y is going to be f inverse of x. Even simpler way is something like this. dy over dx is 1 over dx over dy, just like usual fraction. Its general proof is actually hidden here, and it's not too difficult, but I don't know how useful this will be for most of the students, so I'll simply leave this rigorous proof to interested students only who are going to major in mathematics or something, and then we're going to just use implicit differentiation techniques to answer the other differentiation formulae. First, differentiation formula for natural logarithmic function. How does that work? Well, we have already used this formula and then actually many times, but we're going to do some deduction here. Excuse me. How does that work? Here we go. We begin with y equals to log of x, natural, and then we're going to use inverse functions, so take the inverse. That is, exponential of y is x. That's the equivalent. And then from here, e to the y power is x, we apply the implicit differentiation. So exponential stay the same, and then the derivative pops out. In the right hand side, the derivative of x is just 1. If you're a little bit intimidated by this dy dx notation, then you can do something similar, kind of like this. E to the y power, of course that stays the same, times y prime, because y prime pops out because of this chain rule, and the derivative of the right hand side, derivative by x is just 1. So y prime is equal to 1 over e to the y power. And what is e to the y power, by the way? It's x. So you can deduce it like this. So derivative formula for logarithmic function is 1 over x. However, this dy dx notations are more widely accepted as far as implicit differentiation and inverse functions are concerned. Okay, here's a little bit more practical formula here. If you have a composite function, how do you do? Well, if you use a chain rule, the derivative of outer function is 1 over u. Nothing changes inside, so u just goes there. And then we have to multiply by the derivative of the inside function by the chain rule. So that's what you're going to get. Just application of this rule, 1 over x rule, and the chain rule. But then again, if you do some multiplication to a fraction, that multiplication applies only to numerator. so you end up with u prime of x over u, and this is a practical formula that you should remember. It appears a lot. The other one, if you have arbitrary base, well, basically you can just use change of base formula and deduce them, because log base a of x is log of x over log of a in natural log, and then taking the derivative of that, coefficient is log of a, so we have this deduction. So you can remember this as a formula, yeah, but what I actually suggest is use a change of base formula, kind of like this, and then deduce the formula on your own. So rather than rely upon your memory and then use your notebook, I'd rather recommend you to use your own analytical and critical thinking skill and do put some more effort to your brain. Okay, and we're gonna have chance to talk about a lot of logarithmic functions, so let's postpone that and let's move on to inverse trigonometric functions. And then here are some formulae. Derivative of arcsine function is 1 over square root of 1 minus x squared. Arccosine, very similar except for negative. Arctangent, in my opinion, that's the most important one. The derivative of arctangents is 1 over 1 plus x squared. How about arccosecant? Kind of like that. Arcsecant, similar. And then interesting parallel here. The difference between arcsine and arccosine was just sign, and same thing goes here. Arccosecant and arcsecant differ only by sign, plus or minus. Same thing goes here too. Cotangent and tangent, arctangent, arccotangents, derivative formulae differ only by sign. Let's see, how do you prove that? Well, I'll leave most of them to students, and actually this notebook is posted, so if you want to see the proof or if you want to cheat, you can do that, but let's do a little bit of work. Okay, let's see. This one, let's go with arcsine. Y equals to arcsine of x is equivalent to sine of y equals to x. That's the starting point, and then take the differentiation implicitly. So derivative of sine is cosine, and then as usual y prime pops out, and the right hand side derivative of x is just 1. That's going to be typical for all inverse function. Right hand side will be 1, and divide by this cosine of y. What do you have? Y prime is equal to 1 over cosine of x, and then a little bit of algebraic cosine of y. What am I doing here? Cosine of y. This is correct differentiation formula, yes, but it's not expressed in terms of x, so it needs a little bit of further work. Using Pythagorean identity, cosine is square root of cosine squared, or square root of 1 minus sine squared, and then sine of y is x, so we have 1 over square root of 1 minus x squared. Arccosine will be similar. Start from arccosine, so cosine of y is equal to x. Take the derivative implicitly, then we have negative sine of y times y prime equals to 1, because derivative of x is 1, and divide, again the same mistake here, I apologize again, negative sine of y, and then in terms of y everything's great, but y1 in terms of x, so again Pythagorean identity will come into play. Sine is square root of 1 minus cosine squared, and cosine of y is x, so we have that formula. For arctangent, here it is. Tangent of y is x, and take the derivative. Tangents become secant squared. Right hand side, derivative of x is just 1. Great. Divide, and then we have y prime equals 1 over secant squared. Secant squared is 1 plus tangent squared, so we can manipulate like that. And tangent squared of y is x squared, because tangent of y is x, so we have that formula. I'll leave cosecant, secant, and cotangent problems to students. Just remember to take the derivative implicitly, and then you can do it. Well, some examples are in order. Let's go ahead with using these formulae. So I think it's a good idea to keep those formulae open there. And then let's take the derivatives of some of these. Let's see, I think I'll have time to do just one of them. So let's go ahead and do the first problem, maybe two, I don't know, let's try. Square root of arctangent of x. So this is basically the same as arctangent of to the 1/2 power, isn't it? So if you take the derivative, excuse me, then by chain rule 1/2 comes out, and then inside never changes. We have to subtract 1 from the power, and then we are doing the chain rule, so inside never changes, so it has to be the same as before, arctangent. And then by the chain rule we have to multiply the derivative of the inside. 1 over, what is the derivative of arctangent? 1 plus x squared. Is that true? Let's open up. Yes, that's true. And then here in this notebook I did a little bit further algebraic manipulation to bring this square root notation back, but that final simplification is quite unnecessary. It's very arguable whether the square root is actually simpler than the power notation. Let's see, it looks like I'll have time to do one more problem, so let's go ahead and do that. So let's go ahead to the last problem here. Okay, so this is we have sine function inside, square root, power function, and then arcsine function. So it looks like you'll have to use chain rule twice. So outermost function is gonna be arcsine function, so you'll have to use this formula. So 1 over square root of 1 minus, and then x squared. Instead of x we have to use this, whatever that was the inside. That's the essence of the chain rule. So we have square root of sine of x total quantity squared is what you're gonna get as a outside function, and then multiply the derivative of the inside. Okay, let's take a deep breath and then calculate the derivative of the inside, derivative of this part, and that's going to be another chain rule problem. Outer function is 1/2, so let's see, maybe okay, let's okay, I want to keep the intermediate steps. Okay, what's the derivative of the inside? 1/2 comes out, and then inside never changes. Subtract 1 from the power, so we have negative 1/2 power. That takes care of the derivative of this inside, and then again I'm gonna get another thing to be multiplied, because that's going to be the chain rule. Okay, so this dot 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 should be the derivative of the inside function. That's going to be another chain rule. And finally we have to multiply the derivative of the all the way inside function. That derivative is going to be cosine. So let's express all this as multiplication. And then of course you can do some further simplification if you will. Let's open up and let's see what I already wrote here. And then that's basically it. 1 over, yes, that's the power part, and then the inside part. And the second and third line are just simplifications.